Let us continue D block elements. In the D block elements, we will see crystal structures at room temperature. Before seeing crystal structures in the electronic configuration, where we have got anomalous electronic configuration. The anomalous electronic configuration we got in 3D series chromium, copper. In 4D series, from fifth group niobium to copper family silver, anomalous electronic configuration is there. Then in the 5D series, nickel family, platinum is having anomalous electronic configuration and copper family gold is having anomalous electronic configuration. In the coinage metals, all the elements have anomalous electronic configuration. Okay. Then we will see crystal structures at room temperature. D block elements, crystal structures at room temperature we will see. Now we are taking a third group. Third group contains scandium. Scandium comes under HCP, hexagonal close packed. Then yttrium. Yttrium comes under hexagonal close packed. Then lanthanum. Lanthanum comes under hexagonal close packed. Next fourth group titanium. Titanium comes under HCP, hexagonal close packed. Zirconium comes under hexagonal close packed. Hafnium comes under hexagonal close packed. Next we will take fifth group. Fifth group vanadium comes under body centered cubic. Niobium, body centered cubic. Tantalum, body centered cubic. Tantalum, body centered cubic. Next we will see chromium family. Chromium, body centered cubic. Molybdenum, body centered cubic. Tungsten, body centered cubic. Body centered cubic. Next manganese family. Manganese crystal structure, it is difficult to say, difficult to say. Mixture of crystals, mixture of different structures. Technetium, HCP. Technetium, hexagonal close packed. Then rhenium, hexagonal close packed. Rhenium, hexagonal close packed. Next we will take iron family. We will take iron, body centered cubic. Iron, body centered cubic. Ruthenium, hexagonal close packed. Ruthenium, hexagonal close packed. Osmium, hexagonal close packed. Osmium, hexagonal close packed. Next cobalt, FCC. Rhodium, FCC. Iridium, FCC. Next copper family. In the copper family, all the elements are FCC. Copper FCC, silver FCC, gold FCC. Next zinc family. Zinc family elements structure is typical. That means we are unable to say the structure. It is mixture of crystal structures will be there. That's why. So we have said the crystal structures of D block elements. Next we will go for melting points. We'll take next one is a melting point. We'll take how the melting point will be there. That we'll see. Melting point of D block elements. We'll see. Melting point of D block elements. Now, the melting point, how it is there means the melting point increases along the period. Melting point increases along the period like this. Then it is decreasing at the middle. Again melting point increases, then decreases. Melting point decreases like this. So how the melting point is there means along the period melting point increases, then decreases, at middle decreases, again increases, then decreases. Like that it is there. Sorry. If you take 3D series, this dip, at this dip, what element comes means manganese comes. At this dip, manganese comes. Sir, how the melting point of a 3D series will be there, that we will see. In 3D series, we will take here scandium melting point, titanium melting point, vanadium melting point, chromium melting point, manganese, then iron, cobalt, nickel, copper. Melting point is like this is there. That means melting point increases from scandium to chromium. Why melting point increases from scandium to chromium? Because number of electrons involved in metallic bonding increases. So, which electrons involved in metallic bonding? N-1d and Ns. For scandium, d electrons 1. For titanium, d electrons 2. For vanadium, d electrons 3. Then for chromium, d electrons 5, s electrons 1. So, number of unpaired electrons we will see now. So, number of unpaired electrons 1 here, number of unpaired electrons 2, that means d2, number of unpaired electrons 3, number of unpaired electrons 6. Why? Because d5 s1, 3d5 4s1. Number of unpaired electrons 5 because 3d5 4s2. Number of unpaired electrons 4, here 3, here 2, here number of unpaired electrons 1. Set. Now, generally, metals have high melting points than non-metals. Now, S block, D block, F block are metals. D block elements have higher melting point than S block elements. Why D block elements have higher melting point? Because in D block elements, this D subshell electrons, this S subshell electrons involving in metallic bonding. Therefore, D block elements have higher melting point than S block elements. Sorry. In the D block, if we go like this, from scandium to chromium, melting point increases. Why? Because number of unpaired electrons increases. Sorry. From iron to copper, melting point decreases because number of unpaired electrons decreases. Manganese, what about manganese? Manganese is exceptional. Why melting point of manganese is coming like this? In the sense this manganese is not having particular crystal structure, it is having complex structure. Mixture of crystal structures are there for manganese. For rest of the elements, if you see, particular crystal structure is possible. But for manganese, typical crystal structure, mixture of crystal structures, complex structure it has. Therefore, melting point of manganese is exceptional. It is lower than chromium as well as iron. Okay. Next we will see 4D series we will take. Now we will take 4D series. 4D series melting point we will see. We will compare 4D series with 3D series. 4D series melting point is greater than 3D series compared to respective corresponding elements. 4D series melting point is greater than that of 3D series elements. Okay, that means in the scandium family, scandium, yttrium, lanthanum, actinium is there. Down the group melting point increases. Okay, so yttrium melting point is greater than scandium. Lanthanum is greater than yttrium. Actinium is greater than lanthanum, like this. Now, here what is the exceptional means? Technetium is exceptional case. Technetium comes under exceptional case here. So, like manganese showing dip in the melting point curve, technetium also shows dip in the melting point curve. Then we will take 5D series. Here 5D series, no exception like this. In 3D series, manganese is exception. In 4D series, technetium is exception. In 5D series, like this exception is not there. Sir. Now, in 5D series, melting point, how it is there means greater than 4D series. Melting point of 5D series is greater than 4D series. Like this is there. Now we will see down the group how the melting point is there. Here, here one correction is there. In scandium family, what happens to the melting point down the group in the sense down the group decreases, but in rest it is increasing. In the rest down the group melting point increases. It is exceptional case. Scandium family is exceptional case. Next exceptional case, what means? Copper family. In copper family, how the melting point is there means copper greater than gold greater than silver. Like this is there. In coinage metals, order of melting point, copper greater than gold greater than silver. It is also exceptional. In zinc family, down the group melting point decreases. Down the group melting point decreases. Sir. Now, we will take 3D series. In 3D series, which is having least melting point? Which is having least melting point means zinc, because in zinc 3D electrons in not involving in metallic bonding because it is completely filled. In 4D series, least melting point, which is having least melting point in 4D series means zinc family cadmium. In 5D series, least melting point possessed by zinc family mercury. Okay, so now we will see first in 3D series how the melting point is there along the period means from scandium to chromium melting point increases, then iron to copper melting point decreases, manganese shows exception because of complex structure. Then generally down the group melting point increases in the D block. Exception is scandium family, copper family, zinc family. Now 4D series elements have higher melting point than 3D series elements. In 4D series, technetium shows exception like manganese. In 5D series, melting point is greater than 4D series. In 5D series, no exception as like technetium. Okay. Down the group, generally melting point increases. Exception is scandium family, melting point decreases. Zinc family, melting point decreases. Copper family, copper greater than gold greater than silver. Then what about least melting point in each series? 3D series least melting point zinc, 4D series cadmium, 5D series mercury. In what way melting point is there? In that way only enthalpy of atomization also is there. Enthalpy of atomization is there as like a melting point. Okay. Next we will go for atomic size. Next we are going for atomic size. Atomic radius. We are going for atomic radius. Atomic radius, scandium. Scandium atomic radius 164 picometer. 164 picometer. Titanium 147. Titanium 147 picometer. Then vanadium 135. Vanadium 135. Chromium 129. Then manganese 137. Manganese 137. Then iron 126. iron 126, cobalt 125, nickel 125, then copper 128, zinc 137. So atomic radius is there like this. So it is a 3D series elements. Along the period, atomic radius like this is there. Now we will check this atomic radius order. Scandium to titanium decreases, vanadium decreases, chromium decreases. Manganese is showing exception. Manganese to iron decreases, then decreases, then remains same, then increases. Sorry. Why atomic radius shows like this? Increasing, remains constant, decreasing like this. Which factor playing a role in order to vary like this atomic radius? It is one period, therefore we cannot take number of shells, because in the period all the elements have same number of shells. Principal quantum number will be same for outermost shell for a period. Therefore, we cannot take principal quantum number for outermost shell for explaining the radius. So what are the rest? One is a nuclear charge. Next one is screening constant. Next one is effective nuclear charge. Using this one only, we can explain the atomic radius. We can explain. So now we will take along the period nuclear charge. We will take along the period nuclear charge increases. Nuclear charge is nothing but charge of nucleus, that is nothing but atomic number that increases. Nuclear charge increases. Then along the period, what happens to the screening constant? Along the period, number of electrons in the valence shell goes on increasing, therefore screening constant increases. Therefore screening increases, therefore screening constant increases. So effective nuclear charge is equal to screening nuclear charge minus screening constant. What happens to the effective nuclear charge? That depends on the magnitude of nuclear charge and the screening constant, we can say. Now, increase in nuclear charge decreases size. Increase in screening constant increases size. Okay. Now, we'll take from scandium, titanium, vanadium, chromium. Scandium to chromium, what happens means nuclear charge increases. Screening constant, what happens means increases, but size decreases. Therefore, it is a dominant factor. It is the dominant factor. Nuclear charge is the dominant factor. Then we'll take iron, cobalt, nickel. Here, radius almost remains same. Almost remains same. Here, nuclear charge increases. Screening constant increases. Both are increasing to equal and opposite extent. Therefore, radius remains same. Nuclear charge and screening constant both are increasing to equal and opposite extent. Therefore, radius remains same. Why? Because nuclear charge increases, therefore radius decreases. Screening constant increases, therefore radius increases. Screening constant increases means radius increases. Okay. Here, increase in nuclear charge is equal to increase in screening constant. Therefore, radius remains same. Next, copper, zinc. Here, what happens to the radius means increases. Nuclear charge increases here, screening constant increases. It is the dominant factor. Therefore, atomic radius increases, we can say. Dominant factor is which one? In the sense, screening constant is the dominant factor. Therefore, atomic radius increases. So, now, along the period, what happens to the atomic radius means first, in the beginning, atomic radius decreases, then remains constant, and then increases. So, first atomic radius decreases because nuclear charge is the dominant factor. Then atomic radius almost remains same because nuclear charge is equal to an increase in nuclear charge is equal to increase in screening constant, screening effect. Then radius increases because nuclear charge, that means screening constant is the dominant factor. Screening is the dominant factor, we are saying. So down the group, how the atomic radius will be there, that we'll see. Down the group, we will see the atomic radius. So down the group, we are taking what in the sense? Scandium family. In the scandium family, how the atomic radius will be there, we'll see. Scandium family we have taken. In scandium family, down the group, atomic radius increases. So we are saying down the group, atomic radius increases for scandium family. What about rest? Rest of the family is what? Now we'll take next family: titanium, zirconium, hafnium, rutherfordium. From titanium to zirconium, atomic radius increases. Atomic radius increases. Zirconium and hafnium, atomic radius almost remains same. Almost remains same. Hafnium to rutherfordium, atomic radius increases. Why zirconium to hafnium radius almost remains same? Means in hafnium onwards, 4f14 is there. Due to the reflection of lanthanide contraction, atomic radius of hafnium is almost equal to atomic radius of zirconium. Therefore, in the titanium family, atomic radius increases from titanium to zirconium, zirconium to hafnium almost same, hafnium to ruthenium, hafnium to rutherfordium. Hafnium to rutherfordium, what happens means increases, we can say. In the same way, rest of the groups in the D block, rest of the groups in this D block, we can say. That means this 4D series atomic radius is nearly equal to 5D series because of lanthanide contraction effect, we can say. Next, we will go for density. How the density varies? How the density varies, that we will see. Okay, we are seeing about density. Along the period, what happens to the density? Means density increases. Okay. Next, we will take oxidation numbers. Next, we are taking oxidation states. Oxidation states will take. We are taking oxidation states. Now we will take scandium family. Scandium family, scandium we will take. Scandium shows +3 oxidation number because this valence shell is 3d1 4s2. 3d1 4s2. So scandium shows in the valence shell of scandium 3 electrons are there. Therefore, scandium shows +3 oxidation number. Next, we will take titanium. Titanium electronic configuration is 3d2 4s2. Therefore, it shows +2, +3, +4. 3d2 4s2. Therefore, it is showing +2, +3, +4. In that, stable is what means +4. +4 is stable for titanium. That means valence shell D subshell and valence shell S subshell, both electrons involved in chemical reaction. Therefore, this titanium shows variable oxidation numbers. Next, we will take vanadium. Vanadium shows what are the oxidation numbers, means +2, +3, +4, +5. Vanadium shows these are the variable oxidation states. So, among them, which is stable? Which is stable in the sense +5 is stable. Why vanadium shows variable oxidation states? Means in from vanadium, valence shell 3d orbital and valence shell ns orbital electrons involving in chemical reaction. Therefore, this vanadium family, vanadium shows variable oxidation numbers, we can say. In that, highest oxidation number is quite stable. Next, we will take a chromium family. We are taking chromium. In chromium family, how the oxidation numbers will be there, that we will see. Now, in the chromium family, we will take chromium. Chromium or variable oxidation numbers we will mention +2, +3, +4, +5, +6. Which are stable, we will see. Which are stable means +3 and +6 are stable. For which case? In the sense for chromium case. So for chromium case, stable oxidation numbers are +3 and +6. So most of the compounds of chromium, if you see, +3 chromium will be there. and plus 6 chromium will be there for chromium case. Next we will take manganese. We will take. Next we are taking manganese. Manganese shows variable oxidation states. What are those means? Plus 2 to plus 7, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. Manganese shows variable oxidation states like this. Among them, stable oxidation states plus 2 and plus 7. Stable oxidation states, which one means plus 2 and plus 7 are stable oxidation states. You might have done volumetric analysis. In the volumetric analysis, K-monopore versus FAS titration. In that K-monopore, manganese oxidation number is plus 7. On titration in acidic medium, manganese plus 7 is converting into manganese plus 2. Next we will take iron. Iron shows what are the oxidation states we will see. Iron shows plus 2, plus 3, plus 4. Next we will take cobalt. Cobalt shows plus 2, plus 3, plus 4. So stable oxidation states in cobalt is plus 2 and plus 3. Next we will take nickel. Nickel shows plus 2, plus 3, plus 4. In that stable is plus 2. Copper metals. Copper is having plus 1 and plus 2. Stable is plus 2. Okay. So oxidation states will be like this. In this one, in this 3D series, scandium and zinc showing single oxidation state. Scandium shows plus 3, zinc shows plus 2. Sorry. In this series, manganese shows highest number of oxidation states. In the 3D series, which shows highest number of oxidation states means manganese. Then we will take Fe2 plus and Fe3 plus. Fe2 plus and Fe3 plus we will see which is more stable and which is less stable, that we will see. Fe2 plus and Fe3 plus. In Fe electronic configuration, we will take Fe electronic configuration argon 3d6 4s2. Fe2 plus, if you want, argon 3d6 4s0. Fe3 plus, argon 3d0. Fe3 plus in the sense argon 3d5. Fe3 plus is argon 3d5, we can say. 3d5 is half filled, whereas 3d6 is partially filled. Therefore, Fe3 plus is more stable than Fe plus 2. Okay. Now, down the group, how the stability of higher oxidation states will be there, that we will see. Down the group, how the stability of higher oxidation states will be there, that point we will see. Now, in the iron family, FeO4 2 minus is possible. This FeO4 2 minus is stable only in alkaline medium. Only in alkaline medium it is stable. Then ruthenium family will take RuO4 2 minus. It is unstable. Ruthenium RuO4 2 minus is unstable. Then OsO4 2 minus is stable. OsO4 2 minus is stable, we can say. So down the group, what happens to the stability of highest oxidation state? See, that increases. Here iron given +6 only, ruthenium is +8, osmium is +8. So down the group stability of higher oxidation state increases, we can say. Stability of higher oxidation state increases. One more example we'll see. Then Cr+6 is less stabler than Cr+6 is less stabler than Mn+2, Mn+2, then ruthenium tungsten +6. Okay. So now we are taking chromium family, we are taking. In the chromium family, chromium +6 will take, then molybdenum +6 will take, tungsten +6 will take. How the stability will be there means, the stability is like this. Chromium +6 is less stable than molybdenum +6 and tungsten +6. Now you see, dichromate anion is used as strong oxidizing agent. That means, why it is strong oxidizing agent? See here, chromium +6, that is easily converting into chromium +3. Whereas molybdenum trioxide and molybdenum tungsten trioxide is not used as oxidant. Is not used as oxidant. Okay, dichromate is used as oxidant because it is easily converting into Cr+3, but molybdenum trioxide and tungsten trioxide are not used as oxidizing agents because oxidizing nature is high for chromium, because chromium +6 is less stable than molybdenum and tungsten +6. Okay, that means here down the group, what happens to the stability of higher oxidation state? Increases. Stability of higher oxidation state increases, we said. Okay, next we will see metals undergoing chemical reaction. Generally metals will undergo oxidation rather than reduction. How that oxidation potential will be there? How the oxidation reaction will be there? How the reducing nature will be there? That we will see. Now we will take metal solid, that into metal ion aqueous. Metal ion aqueous. For this, as per this, how the reactivity will be there for D block elements, we will see. Now for titanium, E0 value is given. E0 value is how much? Means minus 1.63 volt. Minus 1.63 volt. E0 value. How to find this E0 value? That we will see. We have to take titanium metal, convert this into gas, convert this into ion, convert this into again ion. Okay. Then what is added? It is taken for hydration. So these many steps you have to consider. For this overall delta H find it, delta S find it, delta G find it, from delta G find E0. Okay. So for this overall we are finding delta H, then temperature we are taking, delta S we are finding, from this ratio we are getting delta G. Delta G is equal to NF E cell. From delta G get electrode potential. Okay, so for titanium electrode potential is 1.63 volt. This what in the sense, for titanium how much means not minus, that is plus. That is plus. Next vanadium case. Vanadium how much in the sense 1.18. 1.18 plus. Next chromium will take, chromium is 0.9. Next, manganese 1.18, iron 0.44. Next, cobalt 0.28, cobalt. Nickel 0.25, nickel 0.25. Copper 0.34, zinc 0.76, zinc 0.76. Okay. Now we have given E naught values given for this reaction. For like this reaction, we have given E naught values. So from this, let us say how the reactivity will be there. How the tendency of metal to undergo oxidation we can say. Now see the E naught. Here for titanium, E naught is plus 1.63 volt. That means positive tendency to undergo reduction oxidation. Vanadium, E naught value decreased. Chromium, E naught again decreased. Manganese is coming under what in the sense? Manganese coming under exception. Iron decreases 0.44. Cobalt decreases. Nickel decreases. Copper decreases. Zinc, copper increases. From nickel to copper increases. Copper to zinc increases. So now along the period, tendency of metal to undergo oxidation decreases generally. Why? Because sum of I1 and I2 increases. Sum of I1 and I2 increases. Okay. So along the period, oxidation tendency of metal generally decreases because sum of I1 and I2, this sum increases. Okay. What about copper? Copper we'll see. For copper, what is a E naught value? For copper, E naught value is minus 0.34 volt. That means oxidation potential of copper is minus 0.34 volt. Why? That means copper is having negative tendency to undergo oxidation because atomization of copper is high, heat of atomization of copper is high, hydration enthalpy of copper is low. Therefore, copper comes under copper oxidation tendency is very low. Oxidation potential is negative for copper. Oxidation potential is negative for copper. Why oxidation potential negative for copper in the sense? For copper, atomization enthalpy endothermic is high, hydration enthalpy exothermic is low. Therefore, copper is having very less tendency to undergo oxidation. So for copper, oxidation potential is negative. Sorry. Next we will see manganese. We'll see manganese coming under exceptional case. Manganese oxidation potential is greater than chromium as well as iron because manganese is getting 3d5 off-field electronic configuration on converting into Mn+2. That's why. Next we will take zinc. For zinc, oxidation potential is very high. That means from copper to zinc, oxidation potential increases. So zinc is more tendency to undergo oxidation. Why is it so? Because zinc converting into Zn2 plus means it is pseudo inert gas configuration, 3d10 completely filled configuration. Therefore, for this melting point, for this oxidation, that means zinc easily undergoing oxidation. So nickel we will take. We'll see about nickel. Nickel 0.25. That means nickel 0.25 in the sense from cobalt to nickel, decrease in oxidation tendency less. Why? Because hydration enthalpy of nickel is high. Hydration enthalpy of nickel is high. That's why. hydration enthalpy of nickel is high. That's why like this happening. Okay, so in the metal to divalent metal ion, that means oxidation. In this oxidation nature, how we have taken, what is the conclusion we got in the sense? Along the period, metal tendency of metal to undergo oxidation decreases generally because sum of I1 and I2 increases. Copper is having negative oxidation potential because enthalpy of atomization is high and heat of hydration is low. Manganese is showing exceptional case. In the manganese, Mn+2 is having 3d5 off-field configuration, therefore it is having more oxidation potential. Then zinc is having higher oxidation potential because in zinc 3d10 is completely filled configuration, that's why. Nickel comparatively, that means cobalt to nickel, decrease in oxidation potential is much less. Therefore, why? Because nickel hydration enthalpy is high, that's why. Next we will see titanium and vanadium with dilute non-oxidizing agent acids at room temperature. How it is there? At room temperature, how it is there? At higher temperature, how it is there? Sir. Now we will take titanium and vanadium at room temperature with dilute non-oxidizing acids. This is a passive because of protective oxide layer on the surface. Now we are taking a what in the sense titanium and vanadium at room temperature with non-oxidizing acids. Non-oxidizing acids means dilute HCl, dilute H2SO4, concentrated HCl, like this, non-oxidizing acids. But we want to take dilute non-oxidizing acids, that means dilute HCl and dilute sulfuric acid. With this, at room temperature, these are passive. That means not reactive. Why? Because the surface titanium and the surface vanadium has converted into oxides due to atmospheric air. So in the surface, oxide layer is there. Due to oxide layer, these are unable to penetrate, so that the bulk titanium and vanadium are not going for chemical reaction. Okay.